Welcome to the Basics of Spectroscopy video series. Let's talk about transitions. Transitions occur when matter changes from one quantum state to another. This can occur via either of four processes: absorption, emission, or inelastic scattering of light, and inelastic scattering with matter. In spectroscopy, we're usually concerned with the first three processes, and these are discussed in more detail in the Masterclass series. In the process of absorption, the atom or molecule gains the energy of a photon and is left in a higher energy excited state. The process of emission is the opposite of absorption. In this case, an excited atom or molecule relaxes to a lower energy state by emitting a photon. The process of inelastic light scattering is also known as Raman scattering. This is an energy transfer process that is a little different from absorption or emission. When the scattering photon interacts with a molecule, it can either lose energy and induce an excitation in the molecule, or it can gain energy and cause de-excitation or relaxation to occur. Inelastic scattering via collision with matter is analogous to Raman scattering, except in this case it is another atom or molecule that gains or loses energy concomitant with the transition. Spectroscopy allows us to measure and monitor the physical and chemical properties of matter by probing quantum structure. A detailed discussion of this is also available in the Chemistry 209 Masterclass series. In a nutshell, spectroscopy allows us to measure the energy gaps between quantum states. We can relate these energy gaps to the frequency, wavelength, and wave number of light via Planck's relation. So spectroscopists often discuss observations in terms of these dimensions. At its most basic level, spectroscopy boils down to A minus B equals C. The challenge is knowing what in the heck A and B are. In other words, how do we determine state energies? The practical answer to this question is that we measure lots of transitions, analyze the observed spectrum, then report the state energies relative to the absolute lowest energy, or ground state. Analyzing a spectrum is usually not trivial, and it requires an understanding of what motions and interactions govern the state that is being probed. Molecules can be in a state of rotation, vibration, or electronic excitation, or a combination of these. Each distinct combination results in a distinct, discrete energy level. We also find that a property known as quantum spin has important bearing on quantum structure. By knowing how these motions influence the molecular energy level pattern, we can reverse engineer observed spectra to reveal numerous chemical and physical properties. I hope that you found this short video on spectroscopic transitions useful. See you next time.